So scientific measurements. When scientists make measurements, they record that measurement in a very particular way so that other people reading those numbers understand exactly what we meant. We record all of the certain digits and one estimated digit. So when we look at a scientific measurement, all the digits we are certain about except the last one, which is uncertain. We include that last digit because it does give us information. So here are two tables of data on carbon monoxide concentrations in Los Angeles County air. This one has 1 decimal place, and this one, the numbers are rounded to the nearest part per million. This data is more precise. This tells us that in 1993, the concentration was 6.9 parts per million. There is some uncertainty in that last digit, probably plus or minus 0.1. So generally the uncertainty will be plus or minus 1 in the last digit, unless it's specified otherwise. It may say plus or minus 0.5, then you go with that. So these numbers then have been rounded. This implies that the uncertainty is in the ones place. So when I look at this, I say, well, this means 6 to 8 parts per million. And this means 6.8 to 7.0 parts per million. This is a much tighter, closer range, isn't it? This is quite a big range. So we need to learn how to deal with the digits in measurements. Any questions yet? So the digits we record depend on the measuring device. Here we have a pistachio on a kitchen scale. We're going to ignore the ounces side because this is chemistry and we're going to use metric whenever we can. So over here on the grams side, this big line at the top says 0, and then there's one down here that says 10, and if you count the red lines in between, there are 9 of them in between, and so each line represents 1 gram, right? So when we look at the movable line, which is telling us the mass of that pistachio, we see that it's between 1 and 2. It's a little past 1 gram, and it's not yet to 2 grams. So if we say 1 gram, is there any uncertainty in that number? No. It was between 1 and 2. We know that for certain. What scientists do is we read between the lines. So this is between the lines. We're going to estimate how far it is between the lines. You may not agree with someone else measuring exactly the same thing. It's okay, there's uncertainty there. So these lines are every 1 gram, and so we estimate the next decimal place. So the certain digit is in the ones, so we estimate tenths. So we look at that and we think, oh, I think it's about, 2/10 of the way from 1 to 2. Somebody else might say, no, I think it's 1.3. That's fine. We can agree to disagree about the uncertain digit, but we will all agree that it's 1 gram and a bit more. Okay? Very, very important. As we're doing experiments in lab, we will be making measurements. This is what's called an analog device. It's not digital. And we use a lot of analog devices, burettes and graduated cylinders and rulers and things like that. When you make a measurement with an analog device, I will expect that you use the correct number of digits, that you read between the lines and estimate the appropriate digit. If you do not, you will be docked points on your experiment. Okay? Yes?
And that would just be to the 10th place, or is that just with this?
It is for this instrument that we go to the 10th place. And so that's why I give you this statement here. Estimate 1 decimal place past the smallest division. So you look at the device and you say, well, what does the smallest actual line represent? Is it 1? Is it 0.1? So on a ruler, most rulers, the lines represent 0.1 centimeters because there's 1 centimeter and there's 2 centimeters and there's 10 lines in between, so they're each a tenth. So if the lines are 0.1 centimeter, then we estimate the next place. Okay? If you can get that into your head, it's easy to remember what should I be measuring to.
So then if we had something that went to like the hundredths place, then we would estimate to the thousandths, so we would
Yep.
have 3 digits?
Mm-hmm. Yep. And if you had a device that the lines were at the 10, maybe every 10 milliliters. So if it's certain at the tens place, then you're estimating the ones place. Okay, so it's always 1 decimal place past what the smallest line means. So the key things to remember here is this statement: estimate 1 decimal place past the smallest division. And this idea, read between the lines. So we estimate between the lines. If the line, what you're measuring is exactly on a line, you still need to estimate the next decimal place. What if it was exactly on 2 grams? We'd say it's 2.0. We are estimating that it is exactly on the line. It's 2.0. And that's where people mess up the most. Because, oh, hey, it came out to a nice whole number. You know, let's do another example here. Actually, 2 examples on this one. So here we have a thermometer. This is, it doesn't show the unit on here, but this is in degrees Celsius. And so the first thing you should do is kind of orient yourself to the thermometer. This line here is 100 degrees. And up here, this is 110. Down here, this is 90. So what does each of these lines represent? 1 degree. So what do we estimate?
Hundredths.
The next from 1 is tenths. Yeah. So we're going to estimate to the tenths place. So we find the red alcohol here, and it's 100, 1, 2, 3. Kind of looks like it's exactly on the 3, doesn't it? It's like right there. So it's 103. 103, but we need to estimate a tenths place. If we think it's exactly on the line, then we'll say 103.0 degrees Celsius. Because if I write 103 without the 0.0, that means that the 3 is uncertain. And I'm just saying it's between 102 and 104, when clearly from this thermometer, it's very, very close to 103. Now you might say, no, I think it's a smidge under, it's 102.9. That's okay. But get the right decimal place written down, okay? This is, well, what is that? I don't think it's a graduated cylinder. It might be a burette. Well, it must be a graduated cylinder because the numbers are right side up. So here we have liquid, most likely water, in, let's say it's a 10 ml graduated cylinder. You see this curved surface at the top? It almost looks like there's a contact lens sitting there, doesn't it? Water does that, and we'll explain why later. But that's called a meniscus, and what we've decided is that we're always going to measure the bottom of the meniscus, and that's how the glassware is calculated. If you measure the top of the meniscus versus the bottom of the meniscus, the difference in this one is about 0.3 milliliters. That's pretty significant. So bottom of the meniscus. So we look at this graduated cylinder, and this big line down here is 4 milliliters, and this is 5 milliliters. So each of these lines represents what? A tenth of a milliliter, right? So this one, the lines were 1 degree Celsius. That's the line spacing. Here, the line spacing is 0.1 milliliters. You see how I did that? Each line represents a tenth of a milliliter. So what do we estimate to? the next place, okay? The second decimal place, or the hundredths. Okay, so this is 4, this is 0.5, and that's 0.6. So it's clearly above 0.5 and under 0.6. So it's 4.5. There's no uncertainty in either of those digits. I mean, the lines are there. It's like parking your car, right? You park between the lines, you're good. There's no like, oh, I don't know. You're in between the lines. It's kind of nice to have lines. But then we need to read between the lines. And so it's like, well, that's a little bit under the 0.6. What do you think? 8? So maybe 8/10 of the way. And so we could call this 4.58 milliliters. Somebody may say, I think it's 4.57. You're right also. Okay? Any questions?
When you measure the meniscus, it's at the very tip, right?
The very bottom.
Okay.
Yep. The very lowest part, it's always going to be in the middle. Sometimes it's a little hard to see, and so especially this one has a nice red background, which makes it easier. Sometimes you need to put your hand behind it, or some people find it helpful to draw a thick black line on a piece of paper and hold that back there, just to help you see exactly where that meniscus is. Yeah, the burettes are they're tricky. So the precision of a measurement depends on the instrument used to make that measurement. When we do calculations, our calculator doesn't understand the precision of our measurements. And when we divide or multiply especially, we can end up with all kinds of digits. And they don't necessarily mean anything. And so to preserve the amount of precision, we have mostly two choices. Differential calculus, or significant figures. Now, there may be a couple of you who would love to do calculus on this. You would get tired of it after a while. Sig figs are actually much simpler. They're not as exact, but they are plenty good enough for most purposes. So we're going to follow the rules for significant figures. So what we identify as a significant figure, sometimes called a significant digit, are the non-place holding digits in a recorded instrument. They include all of the certain digits and the first estimated digit, one estimated digit. So when we make a measurement correctly, all those digits are going to be significant. When you have more significant figures, you have more certainty that your measurement is good. So more sig figs is good. So first off, we need to count significant figures correctly. It's the zeros that give us problem. Any digit in a measurement that is not 0 is going to be a significant figure. And so here in bold are the non-zero digits. That's pretty easy to see. It's the zeros that we have to watch out for. So interior zeros, sometimes I think of them as trapped zeros. Here's an interior 0. Here's a couple more interior zeros. They're sandwiched between non-zero digits. Those are always significant figures. Leading zeros, zeros that come at the beginning of the number, are never considered significant. These zeros, 0.00023, those zeros are there to hold the decimal point. That's all they're doing. They are not implying measurement. This one over here, 0.04268. It's holding the decimal point. It's not an indication of measurement. And you may also notice that, and I want you to try to remember to do this, if you've got a number that's less than 1, always put a 0 in front of the decimal point. Decimal points, especially made with a pencil, can be pretty small and it's easy to miss. The 0 in front of the decimal point causes us to look for the decimal point. Okay, so think about, like if I wrote 0.5. I made a decimal point, but I don't think you can see it. That looks like 5, right? What if I wrote 0.5? Still, the point is too small for you to see. Why would I put a 0 in front of my 5 if it's 5? We don't do that, do we? That suggests to me that maybe the 0 is coming before a decimal point, and it just didn't get dark enough. So we always put zeros in front of our decimal points. This 0 is not something I measured. If I had, maybe I had 6.5 meters. If I put some zeros in front, well, it looks really weird. Does that change the measurement at all? It just makes it look weird, right? I don't really need these zeros for anything. They're not implying a measurement. I could put as many as I wanted, and so that's why we can't count these as significant figures, because then I could just put any amount that I wanted to. So, yeah, we just don't do that. So leading zeros never count, and that's one that students often forget. Okay, so trap zeros, interior zeros, always significant. Leading zeros, never significant. We left the really confusing ones to the end. What about zeros that come at the end of the number? Sometimes they are, sometimes they aren't. So if they come after a decimal point, well, actually, they don't have to be after. If there is a decimal point, an actual decimal point written anywhere in the number, they're significant. So 39.0, that counts as a significant figure. 120.00, all of those zeros are significant figures. 1.432000. Why would I write those zeros at the end? Do I need them to hold a decimal place? No, I've got a decimal point. I wrote them at the end because I measured them and that's what they are. The last one's uncertain, but it's still important, still significant. 29.310. Again, there's a decimal point. So what if I have a number 50 with a decimal point? That's a trailing 0, and there's a written decimal point. Does that count? Yes, it does. Does that number look weird? Yeah, it does. We try to avoid using that notation, but it does come up and we do use it. It would be better to write this in scientific notation 5.0 times 10 to the 1, because then we don't have that decimal point just at the very end after a 0. So trailing zeros with an implied decimal point. These are ambiguous. They may or may not be significant. We can't tell for sure just by looking at the measurement. So we're going to assume the worst. We want to try to avoid them, but if we can't, we're going to assume the worst, and we're going to assume that they are not significant. So the number 300. We don't know if those zeros are uncertain or certain or not at all, or just holding the decimal place. So we're going to assume they're not. So the number 300, the last digit is uncertain. The last significant figure is the uncertain digit. And so this has uncertainty in the hundreds place. So the number 300 means, well, it's between 200 and 400. It's not very precise. 238,100. Again, we need those to hold the decimal place. They're trailing zeros, they're ambiguous, we're going to consider them non-significant. 100,000, same thing. What if this 0 was the uncertain digit? How could we specify that? Well, this is kind of sort of shorthand, which many people understand, but you can't guarantee that everybody will use this notation. Underlining the last significant figure is a common practice. You underline the uncertain digit. But if you want to write this number in a way that other scientists will definitely understand, you should put it in scientific notation. And so then you would write all of those significant figure zeros. You'd leave the last two off, and this would be times 10 to the 5. In scientific notation, if there are zeros, there will always be a decimal point. So in scientific notation, all the zeros are significant. Questions? I think we have some examples coming up here. Oh, we got to talk about exact numbers first. So measured quantities have uncertainty. They have a particular number of significant figures. Exact numbers are exact, and so we say that they have an unlimited number of significant figures. 3 types of exact numbers. Exact counting of discrete objects. So I'm looking at the keys on my key ring. 2, 4, 6. There's exactly 6 keys, right? Is there any uncertainty in that? No, we can count them. 1, 2, 3, 4, 5, 6. There is no uncertainty. So you could write 6.0000000000000 and keep going on forever, keys. Or we could write 6 keys and understand that that's counting of a discrete object. It's exact. So that's one example. Integral numbers that are part of an equation. What does that mean? Well, what if you had, like the diameter of a circle? Dang it. Come on. The diameter of a circle equals 2 times the radius of the circle. Right? Is there any uncertainty in that 2? No. That's an integer number, integral number, in an equation. So the 2 is an exact number. And then defined quantities are exact numbers. So the ones we run into here the most are going to be conversion factors. Some conversion factors are defined quantities, others are not. If we look at 1 foot equals 12 inches. That is exact, because within the English system, they have defined that 1 foot is equal to 12 inches. So if you're using that conversion factor, those numbers have an infinite, unlimited number of significant figures. What if we say 1 kilogram equals 2.2 pounds? Is that a definition? Is a kilogram defined as 2.2 pounds? No, it isn't. So, general rule of thumb, if you are within a given system of units, this conversion is within the English system. 1 English unit of length to another English unit of length. That's going to be exact. This is going between the metric system and the English system. With one exception, that's not exact. If you look up this relationship in different places, you can find it with more or less significant figures. The one that you need to be aware of is that 1 inch is exactly 2.54 centimeters. They redefined the inch to be exactly 2.54 centimeters. So that one's exact. Otherwise, if you're going between 2 systems, not exact. If you're within the metric system, 1 kilometer equals 1,000, 10 to the 3 meters. That's a defined quantity. That's exact. Okay? We'll get some practice with this on the worksheet today. Okay, so practice counting sig figs. How many significant figures are in each number? Letter A, 554 kilometers. 3. So sometimes students will see a whole number like that and think, oh, exact number. No. Think about the unit, kilometers. Are those objects that can be counted? No. That's a length that's measured. Anything measured is not exact. So letter B, 1.01 times 10 to the 5th meters, 3. So in scientific notation, this decimal portion in the front, all of those digits will be significant because you'll never end up with a non-significant 0 or an ambiguous 0 in there. This times 10 to the 5th portion, that's the placeholding part. So those do not count as significant figures. About 1.4500 kilometers. 5. So we've got these trailing zeros. There is a written decimal point, so we count them. So we're going to count all of them, all 5 digits. About 7 pennies. That's an exact number.
Is that what you're going to want us to put? Is
I was
exact?
just going to get to that. So a question like this on a test would most likely be multiple choice. And I won't try to, when I try to trick you, I warn you ahead of time. I'm going to try to trick you about that. I would not try to trick you with this. You could say exact. You could say that this has an unlimited number of sig figs, except I can't spell that. Unlimited, because it's asking how many significant figures. Unlimited, or you could put infinite. Okay, I'll understand any of those words. But don't tell me it has one significant figure, because we can count out 7 pennies without any uncertainty at all. How about letter E, 0.00099 seconds? 2. Those zeros are coming at the beginning of the number. They're leading the way. They are just holding places. They are not measurements. So only the 9s are significant there. How about 21,000 meters? Yeah, technically this is ambiguous. If you said ambiguous, I'd be okay with that. If you were pressed for a number, I'd want you to say 2. Because we're going to assume the worst unless we're told otherwise. But if it's not 2 significant figures, it should be written differently. Okay, any questions? So, in calculations, the result of the calculation needs to reflect the precision of the measured quantities. And so we shouldn't be gaining or losing precision just by doing calculations. And that's the goal of the rules for sig figs and calculations. So there are two types of operations that we need to do this with. Multiplication and division are similar to each other. In a way, they're opposites, right? And so they have the same rule for sig figs. The result carries the same number of sig figs as the factor with the fewest significant figures. So these are the examples. 1.052 times 12.504 times 0.53. Your calculator will show you something like this. To identify which digits you should keep, you're going to go back and look at each of the numbers that you multiplied and identify how many sig figs. So this one had 4, because that's an interior 0. This one had 5, and this one only has 2. And this is the hard part. What's smaller, 4, 5, or 2? 2. So that tells me I should keep 2 significant figures in my final answer. So I'm going to start with the first non-zero digit, the 6 and the 7. I'm going to keep that digit, and then I need to be careful about rounding. I think rounding is going to come up in a slide pretty soon. But so I'll record that as 6.7. Okay. Here's another one, 2.0035 divided by 3.20. Calculator gives us this little mess. The first number had 5 sig figs, the second one had 3. Trailing 0 with a decimal point, that one counts. So 3 is smaller than 5. So my final answer should have 3 significant figures. That 0 before the decimal point doesn't count. That's a common mistake. Students count that 0. Start with the first non-zero digit. So I've got 626. There's my third one. I'm going to round it off there and write it as 0.626. I think it's always a good idea to write down, if not the entire thing that your calculator gives you, at least more than what you need, and then round it off later. Because if you make a mistake rounding and realize it later, you can go back and just round it again correctly. You don't have to do the whole calculation over again. Any questions? Addition and subtraction are different than multiplication and division, and they also have their own rule. So here, the result carries the same number of decimal places as the quantity with the fewest decimal places. So there's a similarity in these definitions. For multiplication and division, it's the fewest number of sig figs. For adding and subtracting, it's the fewest number of decimal places. Okay? So it's helpful, especially when you're first starting out and trying to get a handle on this, to stack the numbers up like you were going to do longhand adding or subtracting. Line them up as you were taught in elementary school with the decimal points in a vertical row, vertical line. Okay? So I've got 2.345 and 0.07 and 2.9975. I'm going to add those together. Add them on your calculator. You can do it in your head, but then check it on your calculator, because it's so sad when you do everything right, but you did the math wrong. That's supposed to be the easy part. So your calculator says 5.4125. So the rule is the fewest number of decimal places. So what we can do here is we can look at which number stops first as we're going from left to right. So this one ends in the second decimal place. So we've drawn a line here. And that's going to tell us where our number should stop. Okay? So another way of thinking about this, let's underline the uncertain digit in each of these numbers. It's the last significant figure. So in that first one, it's the 5. That's where the uncertainty is. Here, it's the 7. And here, it's also the 5, way over there. So if we think about doing this longhand, adding 5 to, what's that digit right there? Well, we have to assume it's 0, but do we know it's 0? We have no clue. And we have no clue what's up here. So when we end up with 5, are we certain about that 5? No. We weren't certain about the 5 to start with, and then we added it to stuff we had no clue about. So 5 is what we write down, but we don't really have much confidence in that. So then I'm going to add this 7 that I'm certain about to an unknown digit and an uncertain 5. Will I be certain about that result? No. So that one's also uncertain. Then I get to this column. I'm certain about the 4, I'm uncertain about the 7, and I'm certain about the 9. Are we certain about that result? No, because one of those digits is uncertain. That 7 might be a 6 or an 8. We're not sure. So I'm uncertain about the 1. Here's a 3. I'm certain about the 3. Are we certain that that's a 0? Yeah, we are. It's not a sig fig, but it's important. It's a 0 because it's holding a decimal place. And then I'm certain about the 9. So when I add those together, I'm certain about the 4. And everything to the left of that, I'm going to be certain about. So the rule is we keep all the significant figures in the first uncertain digit. The first uncertain digit is the 1. Okay? Any questions? Another way to think about this. Some of the things in chemistry, there's like multiple ways to think about them. You don't need to understand all the ways. Find one that makes sense to you and then ignore the others.
So you kept the 0.1 because that's your
First uncertain digit.
okay.
And we want to include that first uncertain digit because it's useful. The rest of them are meaningless.
Okay.
Because if we're not sure that this is a 1, might be a 2, might be a 0, then the 2 and the 5 after that are completely meaningless. Yeah.
Okay.
If we record them all, then someone looking at this result will assume that the uncertainty is way over here, and that's not true. And so then we're being misleading. So another way to think about this is here the uncertainty is in the third decimal place. So we could say, well, that's plus or minus 1 in the uncertain digit. So that's plus or minus 0.001. This is the uncertain digit. And so plus or minus 1 in that digit would be 0.001. Here the digit that's uncertain is in the second decimal place. So assuming plus or minus 1 in that place, 0.01. Okay? And down here the uncertainty is in the fourth place. So plus or minus 0.0001. I'm putting zeros in here to get the 1 in the same place relative to the decimal point as my uncertain digit. So when I look at these values, this one has the greatest uncertainty. And so then my answer needs to be rounded to that uncertainty, to the nearest 0.01. So I'm going to keep the second decimal place. That's a less popular explanation, but it does ring with some people. So let's look at this one. 5.9 minus 0.221, calculator gives us this. We can stack them up like this and do it. We can think about plus or minuses, or we can just count decimal places. And say, well, this one has 1 decimal place. This one has 3 decimal places. My answer should have 1 decimal place. And that works over here as well. This one has 3 decimal places, 2 decimal places, not 2 significant figures, but 2 decimal places, and this one has 4. The smallest is 2, so I round it to 2 decimal places. Okay. Some students have a really hard time with sig figs. The multiplication division one is the most important one because that gives us crazy things that need to be chopped off all the time. Adding and subtracting, especially in the lab, we rarely run into trouble, and when we do, it's just a 0 at the end. So make sure you get the multiplication and division. Try to do this as well. So what about when we round? So when we're rounding, we look at that digit that we're getting rid of, the first one, and if it's 4 or less, we just chop it off. Basically, we're rounding down. If it's 5 or more, we round up. We want to get it to the closest, and so under 5, we round down. 5 or greater, we round up. It's really important that you not change the overall size of the number, the magnitude, when you're rounding. And students do this, and I know that, yeah, it's a thing. Be careful. So let's say we have 145,279. And we're supposed to round that to this place. Is it 145? No. But that's what students sometimes write down. They'll just chop those off. So one thing I came up with over the summer that seems to work is, so when I'm rounding here, I'm going to write down those digits that I'm keeping, and then for these guys, I'm going to replace them with zeros. Okay? 145,000 is close to 145,279. 145 is not. Think of, maybe you've got a nice RV. Well, no, that would be kind of expensive for an RV. A house. $145,279 is the asking price. Let's just round that off to $145. Will you sell me your house for $145? Of course not. You recognize that's ridiculous in terms of money. But when you're dealing with weird things in science class, you just do stupid stuff, right? You know what? We all do stupid stuff. And doing stupid things does not mean you're stupid. It just means you did something stupid. I did something stupid this morning. I knew my battery wasn't good, and I turned off the engine at 7-Eleven. Stupid. Am I a stupid person? No, I'm not. But I do stupid things. But we try not to do stupid things, right? So that's one way to approach this. It's when you're in the tens place or higher that you need to be careful. So here I'm rounding in the thousands place. So when I'm done, that 5 still needs to be in the thousands place. It can't suddenly be in the ones place. Another way to do this is to put the number into scientific notation, and this is the best thing to do. So if I'm going to take this number and put it into scientific notation, I'm going to take the first non-zero digit, I'm going to put a decimal point after that, I'm going to write down the remaining digits that I want to keep. I'm keeping it as a 5 because the next digit is less than 5, it's 2. And so I round down. And then I go times 10 to the, and then I have to figure out how many places did I move the decimal point. Well, there was an implied decimal point right here. It wasn't written, but I knew that that's where it's supposed to be. I moved it 1, 2, 3, oops, got to switch this over, 4, 5 places. So that tells me this exponent needs to be 5, but then sometimes it's -5. And so how do you remember which is which? So is this a big number or a small number? It's a big number. How does Mrs. K feel about big paychecks? Positive. How do I feel about small paychecks? Negative. So if this is a small number, make the exponent negative. If it's a big number, make it positive. Books talk about moving left and right and positive and negative. I can't remember that. You got to find a way to connect them. Yeah.
What would you consider small?
So like 0.0493.
Yeah.
That's a small number. And so we move the decimal point 2 places, 4.93 times 10. So we moved it 2 places, so I'm putting a 2 here. And then I have to decide, should it be positive or negative? Well, that's a small number, so negative. Quick practice in rounding. 5.37, we're rounding to 2 significant figures. So we're going to keep, we're going to keep this. The digit we're getting rid of, the 7, is 5 or greater, and so we're going to round up to 4. 5.43, the next digit is smaller than 5, so we round down. This is 5.3. 5.35, 5 or greater rounds up. 5.349, we look at just the next digit. We look at the 4. The 9 doesn't matter. You only look at the first one. Sometimes students want to start at the end and round all the way back. Way more work, and about half the time you're wrong anyway. It's just the first digit. Okay? We are going to get to some examples here. So to avoid rounding errors, when we have multiple steps in a calculation, we don't want to round at every step. Sometimes those rounding errors can get significant, so we're going to avoid them. We want to only round the final answer, but we have to keep track of the significant figures as we're going along. So don't round intermediate steps. Keep track of sig figs by underlining the last significant digit, that uncertain one. Okay? Now, do you have to write down everything your calculator spits at you? Sometimes there's like 7 digits there. No, you don't. Keep 2 extras. Okay? Keep 2 extras, and you can round the second one up or down if you want to. It usually doesn't matter. Keep 2 extras, and you can just knock the rest off. So in this equation, we have multiplication and subtraction mixed together, and so we need to look at those separately because the rules are different. Okay? So this 5.489 minus 5.01. Do the subtraction, the calculator says 0.479. Apply the rule. The rule is fewest number of decimal places, right? So this number had 3 decimal places. This number has 2 decimal places. So this value here will only have 2 decimal places. So I'm underlining the second decimal place. That's the uncertain digit. That's the last significant figure. But I'm going to write the 9 down and keep that in the calculation so I don't get any rounding errors. When I do the multiplication now of the 6.78 and the 5.903 and the 0.479, this one has 2 significant figures, the 4 and the 7. This guy is just along for the ride. So 2 sig figs, 4 sig figs, 3 sig figs. Calculator shows me this. I have to round it off to 2 significant figures. Because for multiplying and dividing, it's the fewest number of sig figs. Adding and subtracting, fewest number of decimal places. Any questions?
That 9's not included because...
The 9 is included when we multiply, but it's not counted as a significant figure. Because when you do the subtraction, if that's all you were going to do, you would record the answer as 0.48. Because this only has 2 decimal places.
Okay.
But we don't want to round it yet.
Yeah, we just
So
left it on.
we left it on. And you don't, like I said, you don't have to leave all of them on. This one, there was only 1 more digit shown. But if there was, 17 million of them, just keep 2, minimum of 2, and carry on in the calculation.
So what if there was a whole number? There was one that I didn't have decimal point.
So what if there was a whole number? Well, you would need to know why it's a whole number. Is it, times 5 pennies? Then it would have an unlimited number of significant figures because it's an exact number. And what you do with exact numbers in calculations is they don't affect the sig figs at all. If it was 5 meters, a measured quantity, then you'd have to consider, okay, that has 0 decimal places if I'm adding and subtracting. It has 1 sig fig if I'm multiplying or dividing. So let's do some examples. So perform each calculation to the correct number of significant figures. The first thing is just do it on your calculator. 3.10007 times 9.441. Another thing I like about the TI-36X Pro is that you can see the numbers that you actually put in. You can scroll back and actually, like, a whole bunch of different calculations and see what you typed in, so you can double check yourself. If your calculator doesn't do that for you, then I would encourage you to always do your calculations twice, because it's very easy to get a digit wrong, and that'll mess your answer up. I got distracted. Okay. So my calculator is showing me 0.380873,153, which is just ridiculous. You get that number? So the operations we have here are multiplying and dividing. So the rule is fewest number of sig figs. So that first number, how many sig figs in 3.10007? 6. 6 sig figs there. 9.441? 4. 0.0301? 3. Leading zeros don't count. And 2.313? 4. Okay, so 3, oh, that's weird. There's a delay on that. 3 is the smallest. So that means I keep 3 in my answer. So that leading 0 is not a significant figure. So 1, 2, 3, I'm going to keep up to this place. Then I want to look at this next digit. That's the decider. Do we go up or down? It's 5 or greater, so we're going to go up. And we're going to record this as 0.381. Any questions?
Okay, I'm kind of lost. This might
Okay.
be with the professor I had last semester. So whenever we got to that point, it was not the stopping point. It was you move the decimal place so that way your number was between 1 and 10. So it would have been 3.8 times 10 to the negative 1 would have been our final answer. and it was not acceptable to leave it like that.
Okay, okay. My feeling is expressing your answer in scientific notation is never wrong unless you're specifically being asked to show it in decimal. For an answer like this, I would be entirely happy with either. So we could express it like that, or we could put it in scientific notation, 3.81 times 10 to the minus 1. Both of those are perfect answers.
So I don't want to get into bad habits. Do I change it? Like, what do you recommend? Because I'm going to be going further into science classes.
My best advice for what to do is find out what your instructor wants and give them what they want. So I'm giving you flexibility on this. Kind of my rule of thumb for when I write things in scientific notation or not is I look at the number. Typically, I can see 3 zeros with no problem. If there are 4 zeros, I start to doubt my eyes, and I feel like I'd have to get my finger or a pencil out and count zeros, and that makes me feel stupid, and I don't like to do that. So if there's 4, 5, 6, a whole bunch of zeros, either at the beginning or the end, I would prefer to put it in scientific notation because it's so easy to copy down the wrong number of zeros. If there's 1 or 2 zeros, it's easier to write it in decimal, but it's always okay to write it in scientific notation. Does that help?
Yeah.
Okay. So the next one, this is adding and subtracting. Those both use the same rule, so we can just do the whole calculation. 0.881 plus 132.1 minus 12.02 equals, and my calculator shows me 120.961. For adding and subtracting, we count decimal places. Okay, so this one has 3 decimal places. This one has 1 decimal place, and this one has 2 decimal places. So 1 is the smallest number of decimal places, so I need to round this to 1 decimal place. The next digit, the decider, tells me I need to round this up. This is a little bit like the odometer in your car rolling over. If I round the 9 up to a 10, that changes this 0 to a 1, right? And sometimes that can go on and on and on, and you're like, oh, I don't know about this. It doesn't happen too far in this one. So 121. Now I can't just leave off the 0 at the end. I need 1 decimal place. It rounded up so that that decimal place was 0, but that's really important to write the 0. We can put this in scientific notation. We can put 1.210 times 10 to the 2. Okay, either of those is good. Questions? So let's do a couple that are mixed up. So here we've got multiplying, dividing, and adding. So we need to identify what's going on with the adding so that the result of that we can have the correct number of significant figures. You can do this on your calculator using parentheses and just starting at the left and going through. The way I would approach this is I would start with the adding. Are you familiar with PEMDAS? Or please excuse my dear Aunt Sally, right? Parentheses are first. So this is in parentheses, so we should do that operation. 4.11 plus 1.223. I'm going to press equals, and I'm actually going to write down that result. 45.333. I'm going to write it down because I want to identify how many significant figures that sum has. From adding, I go with number of decimal places. This one has 2 decimal places. This one has 3 decimal places. So if this was the final answer, it would be rounded to 2 decimal places. So I'm going to underline the second decimal place. What that tells me is that this number has 4 sig figs. There is a fifth digit written there, but I'm just carrying that along to avoid rounding errors. It's not a significant digit. Any questions about that? So that number is already in my calculator. I'm just going to leave it there. And then I'm going to multiply by this, multiply by, no wait, I can't do that. I'm dividing by this. There's ways around it, but better to just start at the beginning now. So start up here, 2.5110 times 21.20 divided by that 45.333 equals. And so the calculator says 1.174270399. Do you see how my decimal point ended up looking like a comma? I rarely use commas in numbers, because if that number is so big that it needs commas, I'm probably going to put it in scientific notation. And I like to make my decimal points big so that we can see them. So if you see something like that, you should assume that it's a decimal point and not a comma. Because if that was a comma, I would be doing this wrong, right? I'm not putting commas in the correct places. Okay, so this one has 4 sig figs, this one has 4 sig figs, and this one has 5 sig figs, right? So I round my answer to 4 significant figures. There's 1, 2, 3, 4. And then I look at the next one, which decides whether I round up or down. I'm going to round down 1.174. If you had to put that in scientific notation, what would you write? .174 times 10 to the 0. That looks weird, doesn't it? Anything raised to the 0 power is 1. So 1.174 times 10 to the 1 is just 1.174. It's a little silly, but there might be a question sometime that makes you do something like that. Any questions about that one? Okay, let's do this last one. So again, we're supposed to do parentheses first and then add this on. So 12.01 times 0.3. So that part gives me 3.603. If that was my final answer, how many significant figures would it have? One. 12.01 has 4 sig figs. 0.3 only has 1 significant figure. So this would be 1 significant figure. Now I'm going to add the 4.811 plus 4.811. My calculator gives me 8.414. When I'm adding, now I'm looking at number of decimal places. This number had 3 decimal places. This had 0 decimal places. I need to round this to the nearest 1. So I'm going to round this here, and my answer is 8. Any questions?